Good morning to all. I am Prabhavati, Assistant Professor of Mathematics, ADM College, Nagapattinam. Today, we are going to discuss about the topic Laplace transform, which can be defined as follows. To define a Laplace transform, we have to take a function, let us say f of t. So, let f of t be a function of t, defined for all non-negative integers t. Then the Laplace transform of L of f of t is denoted by integral 0 to infinity e power minus st f of t dt, and it is sometimes denoted by capital F of s. That is, that L denotes the Laplace transform which transforms this f of t to the function capital F of s. Piecewise continuous function definition. A function f of t is said to be piecewise continuous in an closed interval a to b, and if you take a point t between a and b, that is a less than or equal to t less than or equal to b, and if we divide the interval a comma b into finite number of subintervals in which each of the function is continuous and it has finite right and left hand limits, then we say that f is piecewise continuous function. Now let me define exponential order. A function f of t is said to be of exponential order if limit t tends to infinity f of t is a finite quantity, that is, should be a finite real number whenever a is a positive number. Now let us discuss about an important property which is known as the linear property of Laplace transform. It is as follows. L of a f of t plus b times g of t is equal to a times L of f of t plus b times g of t. Here f of t and g of t are functions defined for all positive values t greater than or equal to 0, and a and b are constants. So to prove this linear property, first we have considered the left hand side, that is L of a f of t plus b g of t, and we know that Laplace transform of a function is nothing but an improper integral from 0 to infinity into e power minus st function into d of t. Here function is what? A into f of t plus b into g of t. If we replace that function in the integral, we will get L of a times f of t plus b times g of t is nothing but integral 0 to infinity e power minus st a into f of t plus b into g of t dt. And we know that integral is a linear function. So we can multiply and subtract the integral, and we can write like this: a times integral 0 to infinity e power minus st f of t dt plus b times integral 0 to infinity e power minus st g of t dt. And from the definition of Laplace transform of f of t, we find that this first integral is nothing but a times L of f of t, second integral is nothing but b times L of g of t. Hence, L of a into f of t plus g of t is nothing but a times L of f of t plus b times L of g of t. And this property is mainly useful to find the values of to evaluate improper integrals. Now let us discuss about another property, change of scale property. If L of f of t is capital F of s, then L of f of at is nothing but 1 by a times capital F of s by a. Here we are changing the scale t to at. In that case, that Laplace transform will becomes 1 by a times capital F of s by a. Let us see the proof. By the definition of Laplace transform, we have L of f of t is nothing but what? Integral 0 to infinity e power minus st f of t dt. It is denoted by capital F of s. So it will be represented in equation number 1. And now if we replace the t as f of t, f of at, then we have capital L of f of at is nothing but integral 0 to infinity e power minus st f of at dt. Now we are going to use the substitution method. What is that? We are going to substitute that at as some other variable x. So put at equal to x, then what will be your at? It will be nothing but x by a. So here a is a constant. So if we calculate dt, it is nothing but dx by a. If we substitute this in equation number 2, it will become L of f of x, because we are changing at into x. So that left hand side will be L of f of x, and which is nothing but integral 0 to infinity e power minus s. The t is nothing but x by a, f of t is nothing but f of x dx by a. So this will be nothing but, if we take a 1 by a, the constant outside, it will give 1 by a integral 0 to infinity e power minus sx by a f of x dx. And if we replace the variable x by some other variable t, it is nothing but L of f of t 1 by a integral 0 to infinity e power minus st by a f of t dt. And from this we find that in the place of s, we are having s by a and all the other things are same. So this integral 0 to infinity e power minus st by a f of t is nothing but capital F of s by a. So we find the change of scale property. Now let me prove the first shifting property, and it is nothing but if L of f of t is nothing but capital F of s, then L of e power minus at into f of t, it is nothing but capital F of s plus a. This is known as first shifting property. Another one, L of e power at into f of t is equal to capital F of s minus a is nothing but second shifting property. First, let me prove first shifting property. For that, again we are taking the definition of Laplace transform, which is nothing but L of f of t is equal to capital F of s integral 0 to infinity e power minus st f of t dt. It is denoted by capital F of s, isn't it? So let us take this as equation number 1. Now let us replace the f of t by e power minus at f of t, because we want the formula for that. So that I am replacing f of t by e power minus at f of t. So L of e power minus at f of t is given by the formula as integral 0 to infinity e power minus st into e power minus at f of t dt. So now we combine these exponential terms together, we get e power minus a plus s of t into f of t dt. So from the definition of equation number 1, we observe that this is nothing but capital F of s plus a. So again, by the similar argument we can prove the second shifting property. So I am representing here that L of e power at into f of t is nothing but integral 0 to infinity e power at into e power minus st f of t dt. Again, if we combining this Laplace, that is exponential terms in the Laplace integral, it will nothing but integral 0 to infinity e power minus of, I am taking that a minus s, from that I am taking the minus outside, so e power minus of s minus a into t f of t dt. So this is nothing but from definition 1 capital F of s minus a. So L of e power at f of t is nothing but capital F of s minus a. Now let me prove a Laplace transform of derivatives. How to define a Laplace transform for the derivative of the function f of t. So now first I am considering the first derivative of f with respect to t. So to prove this property, first we have to assume that f should be differentiable with respect to t at least one time. If it is like that, then the Laplace transform of f dash of t is nothing but s times L of f of t minus f of 0. So let me use again the definition of Laplace transform. So if we consider L of f dash of t, what will be that? It will be nothing but integral 0 to infinity e power minus st f dash of t dt. Now here we are going to use the integration by parts rule. The last modules we have discussed about this integration by parts rule in the beta and gamma function itself. So I am deliberating use this property here. It is nothing but integral u dv is equal to uv minus integral v du. U and v are functions of t. So here I am going to take that u as e power minus st and dv as f dash of t dt. Then what will be your u dash? It will be nothing but minus s times e power minus st dt, and f dash of t dt is nothing but dv. If we integrate that, we will get the v. So v of t is nothing but f of t. So if we substitute in this integration by parts rule, we will get this. That is u into v. What is u? E power minus st. What is v? F of t. So if we substitute the limits 0 to infinity and minus integral v du. So limit is 0 to infinity. So v is what? V is nothing but f of t, and du is nothing but minus s into e power minus st dt. So now if we apply the limits, we will get, so first limit is infinity. So as s t tends to infinity, e power minus st will become 0. So the first term will become 0, and second term is nothing but e power 0 into f of 0. And we know that anything power 0 is 1. So e power 0 is 1. So the second value becomes f of 0. Again, if we calculate the second, that integral, it is nothing but if we take the minus sign outside and s outside, because we are integrating only with respect to t, isn't it? So we can take that s, we can consider that s as a constant. If we take that minus s outside, then this integral is nothing but plus s times integral 0 to infinity e power minus st f of t dt. So this can be rewrite as minus f of 0 plus integral s times integral 0 to infinity e power minus st f of t dt. This is nothing but L of f of t, and sometimes we can write it as capital F of s. So L of f dash of t is nothing but s times L of f of t minus f of 0. And now using this property, we are going to derive the Laplace transform of derivative of order n. That is, if you have first differentiable with respect to n times or more times, we can find the Laplace transform of f power n of t like this. So the statement is like this: if L of f of t is equal to capital F of s, then L of f power n of t is nothing but s power n L of f of t minus s power n minus 1 f of 0 minus s power n minus 2 f of 1 minus and so on f power n minus 1 of 0. So now let me prove this. For that we are going to apply the previous property, that is Laplace transform of derivative order 1. It is nothing but L of f of d, f dash of t is nothing but s times L of t minus f of 0. In that, if we replace f dash by f double dash, it is nothing but L of f double dash of t, which is equal to derivative of f dash of t first time. So L of f dash of t the whole dash. It can be from the equation 1 write like this: s times L of f dash of t minus f dash of 0, because in the place of f we are having f dash. Okay. So now if again applying the L of f dash of t formula, we will get s into s times L of f of t minus f of 0. If we have multiplied that s inside, then we will get s square L of f of t minus s into f of 0 minus f dash of 0. Similarly, if we calculate L f triple dash of t, it will be nothing but s cube L of f of t minus s square f of 0 minus s times f dash of 0 minus f double dash of 0. So similarly, if applied n times, we will get L of f power n of t. It is nothing but s power n L of f of t minus s power n minus 1 times f of 0 minus s power n minus 2 of f of 0 and so on. Now we are going to calculate an important property, that is L of t into f of t. This is given by this formula, that is if L of f of t equal to capital F of s, then L of t into f of t is nothing but derivative of minus times derivative of f dash f of s, that is minus d by ds of f of s. Again, to prove this, we are going to use the basic definition, which is denoted in equation number 1. That is L of f of t is, again I am repeating the definition, L of f of t is equal to integral 0 to infinity e power minus st f of t dt, which is as capital F of s. If differentiate this equation number 1 with respect to s, we get d by ds of capital F of s is equal to d by ds of the integral 0 to infinity e power minus st f of t dt. Here f of t e power minus st are continuous function, so we can take the derivative inside. They are differentiable, so we can deliberately take the derivative inside the integral. So if we take inside, we have to concentrate that there are two variables s and t, and we are going to differentiate only with respect to s. So in that case, t will be constant, isn't it? So if we take the derivative inside the integral, it will become the partial derivative. So it is become like this. So d by ds of f of s is nothing but integral 0 to infinity dou by dou s of e power minus st f of t dt. Now we are going to differentiate the term only with respect to s. So in that time, t will remain constant. So if we differentiate e power minus st, it is nothing but minus t times integral e power minus st f of t dt, because t is constant, s is the variable. Okay, so that e power minus st or derivative will become like this: minus t into e power minus st f of t dt. So again, if we take the minus outside, this is nothing but integral 0 to infinity t times e power minus st f of t dt. Here that function is nothing but t into f of t. So from the definition of 1, we can find that this integral is nothing but minus L of t into f of t. So we get L of t into f of t is nothing but minus d by ds of capital F of s. Again, if we apply one time, we will get one time differentiation will give you L of t into f of t. So 2 times differentiation, that is if we differentiate capital F of s, again some more time we will get d square by ds square. So if we differentiate second time, the minus will become minus into minus plus. So if we continue like this, we will get the L of t power n f of t is nothing but minus 1 the whole power n d power n by ds power n of L of f of t. That is, we have to differentiate L of f of t, that is capital F of s n times. Now we are going to discuss about Laplace transform of integrals. how to find the Laplace transform of an integral function. L of f of t is equal to capital F of s. Then Laplace transform of integral 0 to t f of t dt is nothing but capital F of s by s. So to prove this, I am going to take that integral 0 to t f of t dt as some other function g of t. So if let g of t equal to integral 0 to t f of t dt. If to find g dash of t, we have to differentiate on both sides. If we differentiate, this g of t will become g dash of t, the integral will be disappear and we will get f of t. Okay, and g of 0 is nothing but 0. If you substitute in the place of t in the integral 0 to 0, if the same limit, the integral will become 0. So g of 0 is 0. Now we are going to apply the previous property L of g of f dash of t. So if apply L of g dash of t is nothing but what? G dash of is nothing but f of t. So L of g dash of t is equal to L of f of t. If we concentrate on the left hand side, LHS, it is nothing but s times L of g of t minus g of 0. So right hand side will be nothing but L of f of t. From this, if we apply the value g of 0 is nothing but what? It is 0. So it will give you that L of g of t is equal to 1 by s times L of f of t. So g of t is, if we replace g of t in this place, we are in the Laplace transform, we will get capital L of integral 0 to t f of t dt is nothing but 1 by s times capital F of s. L of f of t is equal to capital F of s. Then L of f of t by t. So in the previous case, we find the Laplace transform of integral. Now we are going to find the Laplace transform f of t by t. It is nothing given by the integration of L of f of t. Let me prove the result. Again consider L of f of t. It is nothing but integral 0 to infinity e power minus st f of t dt. It is denoted by capital F of s. Let us take this equation number 1. So to calculate the integral s to infinity, we have to integrate on both sides with respect to s and taking limit from s to infinity. So it will give you integral s to infinity L of f of t into ds, which is nothing but integral s to infinity. We are using the equation 1, we will get in the place of L of f of t, we can replace integral 0 to infinity e power minus st f of t into dt into ds, because we are L of f of t, we are having that integral, no? So we are having dt and also we are integrating L of t with ds, so we are having double integration here. So whenever we use the double integration, we are expecting to apply the change of order of integration. Now we can use the change of order of integration in this integral, because e power minus t f of t are continuous function and derivable function. We can deliberately use this. Here if we change the order, that is dt and ds, we will get e power minus st f of t is, the limit also will get changed. So integral s to infinity L of f of t into ds is nothing but integral 0 to infinity integral s to infinity e power minus st f of t ds dt. So if we integrate the first term, what is that? It is nothing but with respect to ds, isn't it? That is e power minus st f of t ds. So we are going to integrate this integral only with respect to s. As I mentioned before, if we differentiate with respect to ds, t will becomes constant. So what term will be get integrated? It is nothing but e power minus st. If we integrate e power minus st with respect to s, in this case t is constant. So e power a minus st becomes e minus t into e power minus st dt. This becomes integral 0 to infinity f of t into integral e power minus st into minus t. The limits will be s to infinity dt. As I mentioned before, if we substitute that infinity in the place of s, as s tends to infinity, exponential term will become 0. So first limit will become 0 and second limit will be nothing but minus of e power minus st minus, because in the place of s we are replacing s only. Okay, so the term will be remain silent. So e power minus st minus t. So for to apply the limit, we will apply the minus, another minus. So minus into minus will get cancelled, will be plus 1. So integral 0 to infinity f of t by t e power minus st dt. So from the definition of 1, we can observe that this is nothing but Laplace transform of L of f of t by t. Thus we get a result as L of f of t by t is equal to integral s to infinity L of f of t into ds. Now let us calculate some standard functions Laplace transform. First one, that algebraic expressions t power n. L of t power n, that is polynomial of degree n, the single term. So L of t power n is nothing but gamma of n plus 1 by divided by s power n plus 1. In the last module, we already found the formula for gamma of n plus 1 and so on. So now I am going to use this here. So to calculate this, again we are going to use the basic definition, that is by definition of Laplace transform we are having that inequality relation, that is L of f of t is what? Integral 0 to infinity e power minus st f of t dt. So if we replace f of t by t power n, this integration is nothing but L of t power n is equal to integral 0 to infinity. In the place of f of t, it will be t power n. So e power minus st t power n dt. Now we are going to use this substitution method to find the value of this L of t power n. So here I am going to substitute st by some other variable u. Then find the value of t. What will be that? It is nothing but u by s, and we have to change the limit. It will be nothing but whenever t tends to 0, u will become 0. When t tends to infinity, u will be becoming infinity. From the definition of t equal to u by s, we will get these results. And if we differentiate t with respect to dt, we will get dt is equal to du by s. Now let me calculate Laplace transform of exponential, that is L of e power minus at. This value is nothing but 1 by s plus a, where provided s should be greater than minus a. What will happen if s equal to minus a? The term will become infinity. So we need Laplace transform to be a finite real number. So s should be greater than minus a. So to calculate this, we are using the definition of Laplace transform. L of f of t is nothing but integral 0 to infinity e power minus st f of t dt. To calculate L of e power minus at, we have to replace f of t in the integration. It will nothing but integral 0 to infinity e power minus st e power minus at dt. If we combine this exponential function, it will be nothing but integral 0 to infinity e power minus of s plus a into t dt. If we integrate this term, we will get minus of e power minus of s plus a into t divided by s plus a, because here t is the variable who is constant, s plus a is the constant, it will become in the denominator. So if you apply the limit integral 0 to infinity, again we are repeating that the same concept, that is that as t tends to infinity, the e power exponential will become 0. So first limit will give you the answer 0. If you apply the second limit, it will be minus in the formula, so minus into minus plus, so 1 by s plus a, because e power 0 is 1. So L of e power minus 8 is what? 1 by s plus a, provided s should be greater than minus a. Now if we calculate L of e power 18, it is nothing but 1 by s minus a, which is provided s should be greater than a. To calculate this, again we have to use the standard definition. It is give you that L of e power 8 is nothing but integral 0 to infinity e power minus s into e power at dt, and if I combine the exponential, we will get integral 0 to infinity e power minus of s minus a into t dt. It is nothing but minus of e power minus s minus a t divided by s minus, if we apply the limit, we will get 1 by s minus a. Now let us calculate the Laplace transform for trigonometric function. For that we need only two values, that is L of cos at and L of sin at. And you will have wonder that is it enough to find a Laplace transform sin at and cos at? And it is definitely true that if we know only the values of L of sin at and cos at, it will provide the answer for the other trigonometric functions. So let me first find the L of sin at. It is nothing but a by s square plus a square. Let me calculate how to find the Laplace transform this sin at. So if we apply the definition, L of f of t equal to integral 0 to infinity e power minus st of t dt. Here f of t is sin at, so this will becomes L of sin at equal to integral 0 to infinity e power minus st into sin of at dt. And we all aware about the definition of this integration of 0 to infinity e power minus sin at dt is nothing but a by integral s square plus b s square plus a square. And now if we apply this Laplace transform of cos at, we will get, it is nothing but a by a square plus b square. It is given by the integration value 0 to infinity e power minus at. Cos bt is nothing but a by a square plus b square. But we need L of cos at, it is nothing but integral 0 to infinity e power minus st cos at. In the place of a, it is s, in the place of b, it is a. So from this formula, that is integral 0 to infinity e power minus at cos bt dt, we will get s by a square plus a square. Now we are going to calculate the hyperbolic functions Laplace transform. So first I am taking sin h at. We are going to calculate this Laplace transform of sin h at. It is nothing but a by a square minus a square, provided s should be greater than modulus a. Modulus a is nothing but what? It may be plus a or minus a. Why we are needing here two properties? Because if s is equal to a, then s square will be a. a square. So a square minus a square becomes 0. If s equal to minus a also, the same case will occur. So for that we are assuming that s should be greater than modulus a. So now to calculate this, we are needing two formulas, that is Laplace transform of e power at and Laplace transform of e power minus at. What is that? It is nothing but L of e power at is nothing but 1 by s minus a, provided s should be greater than a. Laplace transform of e power minus at is nothing but 1 by s plus a, provided s should be greater than minus a. Now we are going to apply the basic formula for sin h at, which is given by the exponential functions, that is sin h at is nothing but e power at minus e power minus at divided by 2. So now L of sin h at is nothing but L of e power at minus e power minus at divided by 2. Now we are going to apply the linear property, which I mentioned before, that this is a very important and useful property we are going to apply here. Here two functions, that is one function is e power at, another function is e power minus at, the constant is 2. So this will give you 1 L of sin h at is equal to 1 by 2 times L of e power at minus L of e power minus at. So L of e power at, as I mentioned, this is nothing but 1 by s minus a. L of e power minus at is nothing but 1 by s plus a. So now this will give you 1 by 2 times 1 by s minus a minus 1 by s plus a. If you calculate and apply the properties of the partial fractions and taking the LCMs, and if you calculate, we will get 1 by s square, 1 by 2 times s square minus a square in the denominator, and numerator will be s plus a minus of s minus a. So minus into minus plus. So we will get a will become 2a and s will get cancelled. So 2 will get cancelled. So L of sin h at is nothing but a divided by s square minus a square, provided s is greater than modulus a. Because this will happen only provided s should be greater than and s should be greater than minus a. Now we are going to calculate L of cos h at. It is nothing but s divided by s square minus a square, again provided s should be greater than modulus a. We are going to use the same technique. We are going to apply that L of e power by at, e power minus at formulas, and cos h at formula is nothing but e power at plus e power minus at divided by 2. So L of cos h at is nothing but L of e power at plus e power minus at divided by 2, and it will again using the linear property, we will get 1 by 2 times L of e power at plus 1 by 2 times L of e power minus at. Applying the L of e power at, e power minus at formulas, we will get 1 by 2 times 1 by s minus a plus 1 by s plus a. If we take the LCMs, we will get 1 by 2 times s square minus a square. In numerator, we will get s plus s minus a. So here a will get cancelled. We will get 2 times s. So 2 will get cancelled. So we will have L of cos h at equal to s divided by s square minus a square. So from this module, we learnt that Laplace transform is useful to find the Laplace transform in improper integrals, and we calculated the linear property and some basic functions, trigonometric and hyperbolic and arithmetic functions, Laplace transforms. And next module we are going to discuss about some problems. Okay, so next time I am trying to use the board to calculate these values, and we can compare the formulas on the cos 80 and sin h 80. Students can easily memorize that, because cos 80 is nothing but s divided by s square plus a square, and cos h 80 is nothing but s divided by s square minus a square, isn't it? So we to learn all formulas, we just to find some problems, we need these basic formulas, and also student can understand that you can just study 3 or 4 formulas, and using that we can, by applying linear property, you can find all the others problems. Thank you.